I work in gamma ray astronomy, and gamma rays at the very, very highest energies of gamma rays. So we find these gamma rays are coming from the most extreme environments in the universe, which are maybe around black holes. The environments around black holes, we call them blazars, will sometimes produce a gamma ray. And so we've identified several new blazars through our work, and also around pulsar winds, which are usually after a star has blown up at the end of its life, gone supernova. We see gamma rays from those environments too. We have a telescope. We have the Veritas telescope. It's built and operated by about 100 scientists who are observing with at the site in southern Arizona, the Whipple Observatory. And we have 4 telescopes. They each have a mirror that's 12 meters on a side. That's about 36 feet. So they're huge dishes, and we image the air shower that's created when a gamma ray hits the atmosphere. The gamma ray comes in, it makes a big shower, and this pulse of light comes down, and we image that pulse of light on the ground through these 4 telescopes. And so that allows us to see the very highest energy photons that are observed on Earth. For me, the photons themselves aren't as interesting as the environment they come from. So we're trying to learn what mechanisms are going on in the most extreme parts of the universe. And these particles are actually, they're created through particle interactions in kind of natural accelerators. So the accelerators that we see around black holes in the blazar environment are just a bit higher than the energies that are at the LHC over in CERN. So we're actually looking at particles that are a little bit beyond what we can study on Earth. And we're learning how black holes accelerate those through magnetohydrodynamics. One of my interests is in cosmology, and so by looking at the environments around black holes, we also learn about the environment of the early universe and what it might have been like. The molecules and things on Earth are actually, the atoms themselves are, there's a lot of iron, there's a lot of heavy elements, and all of those elements had to come out of a supernova in the past. And so the fact is that we are made out of stardust. We're made out of the materials that at one time were in a star earlier in the history of the universe. And that material has gone through the process of a star dying to be synthesized into the things that make up the Earth. And so knowing how the particle physics works in these environments actually tells us a lot about the history of the cosmos. The study of cosmology is fundamentally a study of history. We learn about the very, very distant past. The equations that tell us how the universe got to right now also project into the future, and so we know that in the very distant future that the universe is going to continue expanding, and it's going to get very, very cold, and things are going to get very, very far apart. And so we do know that in another 32 billion years, which is nothing to worry about, that the universe is going to die a very cold and lonely death. Originally, I was going to get into a more useful field where we use technology to solve the world's problems, like climate change. And the very first time I interviewed with a new professor who was working in exploring particle physics and the structure of matter, I realized that at heart I really liked the idea of exploring the universe. And so I totally changed track, and for the rest of my adult career I've been actually looking for things that we've never seen before. And that started in graduate school, where we were looking for the top quark. The top quark hadn't been discovered yet, but we were searching through the billions and billions of events to pick out the very ones that might be the next top quark. And my very first project, I was asked to go look at events with an electron and a muon in our central detectors, and I was looking for muons in the forward, and I found one, and it was probably the very first time we'd ever seen a W boson and a Z boson created in a single interaction of a proton. And so, you know, when we realized this in the middle of the night and we were on the night shift, we just stayed up all night and figured it out and went to the meeting and presented our results the next day. And I was totally hooked. I have to go and look for things that we don't know whether they exist or not. And you know, that continues to today because I'm worked a number of times searching for dark matter, which would be horribly exciting to find the next form of matter that hasn't been, you know, previously discovered. And we've just gone through this exciting time of finding gravity waves and the Higgs boson, and now we're, you know, looking for dark matter particles, and I would love to be the one to find those particles. I mean, there's been 1,000 papers written on the topic that haven't found it, but we keep searching, and that to me is part of the beauty, is to go where no man has gone before. A little Star Trek there for you. So. What we know from cosmology is that there's about, if you look at all of the visible matter and the matter that we know, that we've studied in a laboratory, that we've actually been able to get our hands on and look at in the previously, that makes up about 20% of the total matter in the universe. And the other 80% is the dark matter. And so when we think about galaxies and how they form, they're drawn to the dark matter. The dark matter isn't much drawn to the galaxies. The big behemoth that's making structure in the universe is the dark matter. And so what we know about it is that it's out there. We can measure the kinematics of the motions of galaxies and see that these galaxies have more matter than we can see, but no one's ever been able to get the dark matter to interact and do something that produces light. So we've never been able to actually study it. And so that's why we want to discover the dark matter, is to see the structure, the particle that's actually creating most of the structure in the universe. Most of the things that you're seeing now, the new discoveries are always pushing technology past where it could go 10 years earlier. And we are at a point where technology is progressing very fast forward. And you know, not only the technology of the devices themselves, but the technology of storing the data on disk and being able to get a computer to go through it fast enough to analyze it. And so the fact is that all this, you know, collecting the information is tricky, and then processing the information is also very tricky. And so, and it just requires technology that we have now, and we didn't have it before. And so you're going to see more discoveries because technology continues to go forward. We haven't met the limits of being able to discover new ways of measuring things. I do believe that the cosmos has an aesthetic which maps itself very well onto mathematics, and mathematics itself is a beautiful topic. You know, when you figure out mathematics, you can use it to predict other features of the universe or things that are actually true. And so, you know, to the extent that we love the finding truth and seeing beauty, to me, I see those in the cosmos as well. And there's just, I mean, you can appreciate it mathematically and the beauty that it has, but you know, if you happen to be somebody who likes the equations, but you might also just find that, you know, all those Hubble images that have been coming out for the last 25 years are just, you know, spectacularly beautiful. The universe really is an interesting place. And we see it differently today than they saw it 100 years ago. Before they had the telescopes, you know, they didn't know what the universe looked like, and now we see galaxy after galaxy. I do think that the human spirit actually comes to life when we look at, you know, things that are beyond what we ate this morning, or do we have enough clothes to put on, and that the universe gets very beautiful when we are allowed the opportunity to go and study it. You can't predict what will be discovered. You have to wait and keep looking for it. And I guess if there were students listening, I would want to encourage them to keep on their path, because it always seems like a very lofty goal to suddenly become, you know, an explorer of the universe in this new world of technology. And you know, every little step just takes you there. You don't have to plan to become an explorer. You just keep working at doing things that you think are interesting and fun, and pretty much the next thing you know is you are an explorer.